So bucket one is the corporate procedure, the first box.
Yeah.
And how do we classify instruments? And by critical instruments, I mean SIFs, any instrument used as a protection layer, LOPA, low integrity protection layers. And then you'll have other stuff you want to spend money on. Fire and gas needs to be tested. Uh, E-stops need to be tested. Your rotating equipment, machine protection systems need to be tested. So all of those just become, all right, we need to roll out a mechanical integrity program. We want to manage what instruments you use in those applications. And there's another slush fund of things that make sellable product. It's not in a LOPA. It's not one of these other prescriptive things. The other bucket would be, and there might be burner management systems if you don't pick SILs, but it's still important. Those all fall in there. And that decision tree there is to do a criticality review. So once I have the procedure in place and I have the definition of what's a critical instrument, if I'm at a brownfield site and I test 20,000 instruments, you go through and review each one, just like alarm rationalization, and say, what bucket is it? Is it BMS? Yes, it needs tested. Is it fire and gas? Yes, it needs tested. Is it a SIF? Yes, it needs tested. If you go through and it doesn't fall into any one of those buckets, you can make a decision potentially to run to failure, change it like a light bulb. So by setting the criteria in place and reviewing what you're spending money on today, some subset of things, if it does fail and isn't catastrophic to the business, you just stop PMs on it, if you will, and run to failure, replace it when it breaks. Anything that we decide we want to keep, well, bucket 4 is what data we're going to collect so we can do this prior use analysis. Step 5 is we need to get a starting point failure rate. That could be a assumed generic, though we made an engineering design. It could be a number from the OEM as part of the SIL certificate. I just need a starting point. 6, 7, 8 is getting data in. 9 is actually setting up minimum time in service, which we're going to go through. So when do I have enough data? When can I know it's time to go calculate a failure rate, a potential failure rate to decide if I like it? And 10 is what everybody thinks is hard, which is failure classification to get consistent data coming out.
Yeah.
It's not, we covered it last time. I think John's got a slide on it. Update your test plans if necessary to get failure classification in it so that any tech doing the testing, whether it's your crew on day shift, your crew at night shift, third-party crew you hired in the outage, all gets the same results. Step 12, collect some data. Step 13, when we have enough time in service, calculate failure rates. Do your sensitivity analysis, that feedback loop for safety. Which functions pass, which functions fail. If it passes, how far can I move tests out? Do I like it? Do I not? If I like it, you promote it to the master library. If not, you circle back around and keep testing more until you get some more data to validate what you're doing. But the whole concept is at some point in time, you are transitioning from an assumed failure rate or a OEM failure rate to your failure rates with your instruments, with your maintenance practices, with your instrument installed in Alaska seeing minus 70 degrees Fahrenheit or in Saudi seeing 152 degrees Fahrenheit in the shade versus et cetera, et cetera. You've got your data in your calcs. That's the concept of prior use and progress. So start somewhere and transition to getting your numbers. And I'll do the teaser. You can actually potentially save significant money. So depending on how your boss and management wants to look at it, it's like, well, we can be compliant. We can get this closed loop for safety. We can get line of sight on performance. And oh, by the way, save money. Or we can be, look, I can save a bunch of money. And oh, by the way, do some compliance stuff. So depending on what they want to hear, you can do either or. But management might be most excited about the hard savings, not soft savings. Hard savings, checks they're not writing. And we'll go through some of those calculations in a little bit.
Yeah. So there's going to be some setup cost to this, but what you're saying is that's easily offset by what you're going to gain on the
the net present value calcs I put some ludicrous project costs in there just to show that you could spend millions on setup and it still has strong ROI. And management would potentially be jumping through hoops to go realize the benefits because the benefits are ginormous. There's in this little prior use and progress, there's 2 ways to save money. Anytime I'm in bucket 3 and I decide to run something to failure, well, I'm not testing that annually. I'm not calibrating it annually. I'm not inspecting it annually. We decide it's not impactful to the business and I don't need to continue that spend. So anything that we can get out, that's the gift that keeps on giving. And then once we have our own failure rates, you're going to identify bad actors, things that have dangerous undetected failures that are exposing the business to risk that could escalate if other layers fail. So you're removing that risk from the business, but then you're also finding where your initial assumptions were conservative, and you can start extending testing without, I'll say, putting the business at risk, whether it's commercial risk or actual, safety or environmental risk. You have direct line of sight on all that.
Yeah.
So this is a data-driven approach. You're testing the instruments anyway. The big difference here is just get consistent data coming out and do the black box math that everybody seems scared about, that we'll touch on in a little bit.
Yeah. And as a reminder, this is what the standard requires anyway.
Yeah, this is all shell stuff. This isn't Mike-isms spouting something weird and strange. There's a perception that if I buy a certified widget, I'm done.
Yeah.
And that's not the case. And we covered it in the first slides in the first deck. So go back and look at that if you haven't seen it. I can easily buy a certified field device, a transmitter, right? Pressure, temperature, levels, flow, all those things generally exist. When we get into final elements, a lot of valves don't have SIL stickers. Motors, last I looked, you could get a SIL 3-rated motor contactor for like 25 horsepower. But if you have 250 horsepower, 2,500 horsepower, you're on your own. There are no SIL stickers on that stuff. So what does that mean? Shut your plant down, wait for somebody to make a certified widget? No, you're going to have to make an engineering judgment on a conservative initial starting value and do this prior use and progress thing, which you have to do regardless. So not every field device has a sticker, and that's okay, right?
Yeah. Okay, let's move on from the prior use in progress. So that was kind of a reminder of. I don't think we finished on this.
About this.
We didn't finish on this slide last time, but it was kind of towards the end, and it maybe got a bit rushed. But let me just come off the screen here because I think I'm in the way of some of it. Did you want to cover failure classification, Mike? I don't think we covered this slide at all last time.
No, we did it for a valve, I think, a little bit, but basically what we've got is I need to know, what are you not doing today with testing? You got a piece of paper on a clipboard. Somebody goes out there and scribbles on it and puts a name, date, and says it passed or failed. Well, are we really getting good data coming out? That's where everybody thinks is hard. So we've got to decide, are we going to track systematic errors or not? Are we going to keep up with systematic failures? Systematic failures is difficult. Let's be really blunt. I can say something's a systematic error, and John can say it's a random hardware failure, and we're both right. So you've got to be very, very clear about this. If we want day shift, night shift, and third-party instrument crews all to get the same answers, you need a little decision tree associated with your test plans, and this is a pressure transmitter. And it just says start, and then we're going to go test it. I didn't get into tests and steps and what's in there, improve test coverage, but we just pretend that this is plugging service. And if we found a plugged tap, well, that might be a systematic failure, and I could put a failure code and failure mode and mechanism on that if I wanted to. Or we could do less if that's too advanced for us as an organization and still get the benefits. But systematic implies you're going to change how this instrument is installed, and we will never see plugged taps again because it's an installation error. It's a design error. If I make a change, I can eliminate this failure from the business and we'll never see it again. If you're not going to change the installation, you're going to leave that same instrument in there. Well, that's not a systematic error. That's a, dangerous undetected failure found through testing. And that's where the gray area comes in. There's a Nomura white paper on valves. And basically, if you look at what Nomura has done with their white paper on valves, valves never fail. I think it's like 2 fits, 5 fits, some ridiculously low number, because if it doesn't close fast enough, it's my fault because I didn't specify enough torque or high enough instrument air pressure. If it leaks, it's my fault because I specified the wrong material of construction from corrosion erosion. So that all sounds good, but if I'm not changing that valve out, and that's the same valve we're going to use forevermore, well, those are not systematic errors. They're going to be things we're going to see continuing through the kit, and you'd have to deal with that. So systematic is one thing to tackle. I will say there is one large company that is European based that has tons and tons and tons of prior use data. And they've just decided that they are not going to screw with tracking systematic. It is too difficult for the business. They're not messing with it. So if they see a failure, it's always a dangerous undetected failure found in testing. They put all the systematic stuff in the bucket. In theory, their failure rate should be crappier. And what they found is with their giant gene pool, it's not driving anything. It's not penalizing them. They're still better than, for instance, the ARITA data set with their numbers. So you could start out under keep it simple, stupid, and ignore systematic. What this is saying is for a transmitter, there needs to be a tolerance, a pass-fail tolerance. Keep it straightforward and simple, do it in engineering units. And this is saying it's a high pressure trip at 100 PSIG, 95 to 105 is a pass. Anywhere in there is a pass. You want that band as big as possible so you get as much as much passes. If it's too tight, if it's plus or minus 0.1%, because that's what you bought, well, you might get a bunch of fails. That drives testing, etc. So you really need to look at your safe operating limits tables and set those thresholds so you're not overlapping the alarm and the PPCS interlock and the relief valve with these overly broad pass-fail windows. So there is some judgment required in all that. But if you look up there, if I have a high pressure trip and I trip below 95 PSIG, that's a safe failure. That tripped early. It's a nuisance trip. Might have cost us money. There's no hazard there. If it trips greater than 105, it's higher than we want. It's eating into response time. We could have process safety time connotations. That's a dangerous failure. If it doesn't trip at all, that's a dangerous failure. If I ignored systematic and just had 95 to 105 and safe and dangerous, I can get consistent test results and I can use that same exact level of data in these prior use calculations. That's a sample I have for an unsophisticated end user. I actually have a real project stuff I brought in. And these things flip. Low trip, well, less than 95. Think of vacuum, right? Ooh, that's more vacuum. Well, that's a dangerous failure if I trip below the trip point. If it trips high pressure, greater than the trip point, well, that's safe. It tripped early. So these safe and dangerous box is flip on low pressure versus high pressure. But it's not hard. It's relatively straightforward. You just need to get this captured, document it in your test plan, and get your folks trained on it.
And what's your view on
reduce subjectivity in the testing, if you will?
What's the view on the on tracking things like detected failures? So
detected failures, dangerous detected failures. I would track those as well. It's required in the standard. I want to know what's going on. For instance, if I had two transmitters and I compare them together, and we've got 100 millisecond scan rate on the control system, in the safety PLC, you're having a test basically that's saying, do these two vary by plus or minus 2%, 5%, whatever the number is? It's happened every 100 milliseconds. That's a phenomenal test. That makes lambda DU 95% lower than what you've got. That's finding it when it occurs instead of waiting for testing to find it. It's a cheap insurance policy. You should do it all day long. And we want to track those. If we're seeing those failures, we might need to be changing devices, depending on whether it's a trip or just an alarm. It's not changing your achieved risk reduction factor because lambda DU is not being tweaked, but it is potentially got cost connotation on production. But you want to track those. You want to get line of sight on that. If something's having dangerous detected failures every other week, you're going to want to start changing things. Same thing.
Yeah.
So this is classification. You think a valve, overly simplistic on a valve, what is it? It's got to close fast enough, right? If it's high pressure close a valve, well, the response time is 10 seconds. If it closes faster than 10 seconds, it passed. If it closed slower than 10 seconds, it failed. It's that simple. Not every valve needs tight shutoff. You might have bought it as tight shutoff. There's got to be a process safety connotation on seat leakage. So if there is a process safety connotation seat leakage, same thing. What's your tolerance on seat leakage? When is it a fail? When is it a pass? So this is not hard stuff. Syntef has a lot of documentation on this. There's stuff in ISO 14224. There's also an IEC standard. The ISO 14224 gets very complicated. I'm a keep it simple, stupid guy, so I'll show you the bare minimum data in a second.
Was this the Syntef document you were mentioning?
Yeah, and if anybody, it's free. It's on their website. Yeah. If anybody wants a link, you could, in theory, ask for it or something, John. You can post it in the comments a little bit. But
if anybody,
what they're basically doing, they're saying, hey, once we get in the operate and maintain phase, the next 30 years of my plant, what's important for functional safety, and that's what they're covering in here. This little table, if you follow along with your cursor, this math is in the table. What you do is you take a pressure transmitter, you have the number of pressure transmitters I have at my site, and this is why I'm going after critical instruments in the prior use and progress. If I only have 50 pressure transmitters in SIFs,
Yeah.
but I have 500 pressure transmitters in SIFs and LiPo and BMS and fire and gas and ESDs and making sellable product, production quality, everything else. There's 500 things we test today. Same test plan, same failure classification. Just get data out of testing you're already doing. And what this says is there's an assumed lambda, 7.61 times 10 to the minus 7 failures per hour, or 150 failures, 150 years to fail.
Yeah.
And what this is basically saying is if I have 150
that's a lambda for one device, assumed, yeah.
Correct. That's a lambda for one device.
Mm-hmm.
And the little table over the years, it says if I have 1 year, I need at least 150 devices. If I have 2 years time in service, I only need 75 devices. So I got 500 devices. If we collected data on this, I'd have statistically valid data in 1 year, and I could update failure rates. It's relatively straightforward, relatively simple. It's just saying, get some data coming out of the instruments you're already testing. And to do that, I just need failure classification.
Yeah, so I must have been
what's a dangerous failure?
When you and I first talked about this, my assumption, because I had never done these calculations, my assumption was you needed kind of decades of experience with a device, but of course that's failing to recognise that you might have hundreds of them.
Well, that's just it. I mean, that's what I'm trying to get at is you're testing these anyway, right?
Yeah.
Just get something more than a handwritten chicken scratch with Timmy's initials and a date on it. While you're there, get them to go through that decision tree, find out if it's passed with consistent criteria, find out if it failed. Because if you don't have the criteria in place, like a valve, we had valves in Alaska that wouldn't stroke, and they beat on them with a hammer, tapped on them with a hammer a couple times, stroked them a couple times, and it passed, and ta-da, it passed. And that's what all you see. If you start talking to them about it, well, yeah, it wouldn't go initially, but we had to move it, but we eventually got it to pass. And so they're just putting the pass at the end. It's like, no. If that thing sat there for 5 years and I asked it to de-energize and it doesn't move, that's a fail. We've got to do something about that. We can't be tapping it with a hammer to get it to go. And so if you stress this and the importance of it and where we're at and encourage them, I need you to find failures. Aging kit's got to fail. It's not a reflection on poor maintenance. It's a good maintenance program because you're finding the failures before the demand and you're removing risk from the business and it's working like it's supposed to. So a lot of this is a cultural thing. The guys think, if poor maintenance practices, if we have all these failures and I don't want to show them off, so they end up keeping 2 sets of books. You got to work through that culturally, but it's relatively easy and straightforward and it's not hard and you're doing the testing anyway. Just get some data coming out.
And I think we mentioned, or at least somebody provided a bit of feedback last time that it's making sure that you're recording that correctly, recording the as found condition, not just not shuffling stuff under the carpet.
Next slide is I might want to jump into the math. I've got
next slide. I think it's going into savings. Yeah.
Let's do the math. So
okay,
if we can
got the
share
screen ready, I can.
Screen. Let me get the
screen
one
should
up
already be shared. I just got to switch around
all
here.
right.
Okay.
All right. So what we've got is I've got raw test results. You can see down here in a tab, I've got data from 2021, data from 2022, data from 2023. So we tested it on day 0, we tested it on day 365, and we tested it again, that last time. So it's really 2 years time in service. And you can look at, I hid the tag numbers, so we won't discuss what that is, but you can see that I have 79 devices in this 2023 data set.
Can you zoom in a bit, Mike?
Oh yeah.
So we can. That's a bit.
Holler when it's big enough.
Yeah, that should be okay. Thanks.
All right. So I got 79 field devices, and we're just going to go up here and I'm going to talk about what we got. I have in this 79, I have a mechanical temperature switch and a mechanical pressure switch. There's a trip point, which magically happens to be 150 PSIG, 150 degrees Fahrenheit. That just is how it ended up being for this particular thing. Okay. What we're looking at is positive displacement pumps. There is no relief valve at the discharge of this PD pump because they're making product. And let's pretend it's paint. And if it's red paint and in that dead space under the relief valve, red collects. The next time they want to make blue, the red bleeds in. The next time they want to make brown, the blue bleeds in. So they can't have the relief valves in there because it screws up product quality. So they're doing all this with instrumentation. High pressure or high temperature, trip the pump.
Yep.
So first thing we did, we set a tolerance. And so this ended up being 45 to 155, again, magically PSIG or degrees Fahrenheit. And I'll go see if I've got a failure hiding in here. Let's go to year one. I think I got a failure early. And that tolerance was set up with looking at other protection layers, alarms, and everything else to make sure this was big enough to where we limited the not the 0.1% accuracy because that's what we bought. So we had this big 10 degree or 10 PSIG window. And you can see that on this particular date in 2021, it tripped at 160 PSIG. It's outside the window because it's greater than the upper limit and it's a high trip. We found our first dangerous undetected failure. Mm-hmm. This one tripped low, right? So this is tripped at 144. 145 is our low end. So I had a nuisance trip here.
Yeah.
So we had a safe failure. And so basically just simply using the pass fail criteria with a tolerance, we classified all the failures. They did not want to keep up with systematic. They didn't want to deal with that. They weren't sophisticated enough. They didn't think they could keep it consistently going forward. So we ran this pilot. They have 274 PD pumps. We only had data on 79 to 77. So I had year one worth of data, year two versus the data, year three. I actually calculated time and service for each one of these widgets. And you can see that some instances we tested 2 days early, some days we were 1 day early. They were doing pretty good on testing on time. There's a couple things where they were 10 days early, no big deal. What ended up happening is in year one for pressure switches, I had 263,000 hours time in service. Year two, I had very similar numbers, 760 versus 232. Temperature switches, because they removed some, I had 419,000 hours time in service in year one versus 379. Had lots of time in service when we looked at this with regards to, what are we doing?
Yeah.
So next thing is we just look where we're at is classified amongst this on temperatures. I had 3 dangerous undetected failures. I had 1 safe failure. I had 5 dangerous undetected failures for the pressure switch, 1 safe failure. So we had 8 failures total, dangerous and 8 and 2 safe. Okay, sound like little numbers. Now let's do some math.
Yeah, I skipped to the wrong screen there, Mike. John? Sorry, could you just zoom that in a little bit? That's it. Thank you. Yep. I was trying to find another button setting, and I flipped you over to the wrong screen.
What we're doing. So really what it is this is just, I have pass-fail criteria built into the test plan. I use Excel to find them, and then I just came up with the failures. Now I got little tiny numbers, right?
Yeah.
These are little tiny numbers of failures. So are we good? We bad? How do we, in that feedback loop for safety, where are we? So what we ended up doing is, there's the 77, because they ended up 79 in the 1 year, but then they deleted them. So I discounted the
data. Could you zoom in again?
77. All right.
Thanks.
The failure rate for these guys was 20 years. Okay, we can turn that into that. So I have statistically valid data. If I had 20 devices in 1 year's worth of testing results, I had 77 devices and 2 years cumulative testing results. So I had plenty of data accordingly. And this was early on. So I was debating Bayesian versus Gaussian. So we'll go into the mystery and magic of Bayesian and Gaussian. So I put this reference in here. I cut and paste this in here so you guys could see it. That's the CINTEF report, Guideline for Follow-up of Safety Instrument Systems in the Operating Phase. That's the document to look for. Hiding in this document is the Bayesian math. So you have a conservative estimate. You're using some data to come up with the new number, if you will, the failure rates. And it's doing these 2 values, and it's got all of the math, all the terms, all the formulas, and it's got a sample problem in there, so you can build this out yourself and see if you get the same answers as them, which I did. And then I just applied it to this particular project. So I don't have a pretty spreadsheet. This is Mike playing, right? So I have an initial starting failure rate, which comes up to a PFD average of approximately 2, a risk reduction factor of 2. Risk reduction factor of 20. And then I go through in period 1 for the 263,760 hours time in service with my 5 failures on a pressure switch. It's calculating a new failure rate. And it's saying we were crappier than we had first assumed. We assumed a failure rate of, initial failure rate of 20 years with that 5.70 times 10 to minus 6. It achieves a PFD with a 1-year test interval risk reduction factor of 20. That risk reduction factor drops down to 8.36. The way Bayesian works is you do a first bite of the apple and then you do a second bite of the apple. The second bite of the apple, it's almost like coarse and fine. Now we're doing confidence intervals and other things, and you can see that I'm starting with this failure rate as the one I'm dealing with, and then it goes through and puts a 90% confidence interval on it and some other Bayesian magic. And my new achieved risk reduction factor with the new failure rate for pressure switches is 17.31. So we actually went down. We got crappier for pressure switches than the initial design assumption from the corporate standard. There's also a nice little thing here is that the Bayesian math includes confirmation with statistically valid data from another way. As long as this number is greater than 1.0, we have enough. As long as that number is greater than 1.0, we have enough. So I was able to do 2 observation periods. If you look here, there's observation period 1, observation period 2. And as you get more and more data, they fine tune and things start leveling out. And I did the same thing for the temperature switches, and we're just gonna look at the results. We had a risk reduction factor of 20 with the assumed failure rates with a 1-year test interval. And after this, we moved to a risk reduction factor of 37 with a 1-year test interval. Failure rates got better on the temperature switches. So slightly crappier on pressure, way better on temperature. As part of this project, they had not really ever done a LOPA. They had a new risk matrix. So we went ahead and did a risk matrix, did a LOPA worst case scenario, assigned targets to this. And even though we had a crappier pressure switch number with a 1 out of 2 vote to trip between the 2 devices, I could still extend testing. I did Gaussian math for grins and giggles on this as well. I also calculated safe undetected failure rates so we could deal with nuisance trips and architect constraints and all the other hoo-ha. But I kind of hid all that in the spreadsheet just to keep it simple, stupid. This is all confidence intervals, 50, 70, 90, 99. What am I going to deal with confidence intervals? And you can see if I pick a 70% confidence interval like it's discussed in 508, I get a risk reduction factor of 17 in the Gaussian method for pressure switches versus it was roughly 17. It was 17 on the other one as well, and I get a 39 with a confidence interval of 70. So here's my summary. Bayesian, I get pressure switches with depending on where I'm doing what the test intervals are, which is looking at the 90%.
Can you zoom into this one, Mike, for me?
Sure.
Thanks.
I'm getting risk reduction factors of 35 and 75. I'm getting 17 and 19 with 70%. If I go apples to apples with 90% confidence intervals on the Gaussian, I think this drops to 13, this drops to 28. Bottom line is I collected data. I analyzed the data. We did this in arrears. We had chicken scratch, so it wasn't like we changed the test plans. We classified the failures after the fact, ran the results, did a sample LOPA, and was able to show that we could, with redundancy and diversity of devices and actual failure rates, move testing out. And we'll come back to the money savings after the fact.
Yeah.
So this is easy to do, straightforward.
So summarizing it, then you're collecting failure rate data. You're analyzing that failure rate data using known formulae that have been provided by people that have studied this stuff. And you're coming out with results that allow you to extend your test interval. Correct.
Now I'll get a little bit of commercial on this,
which will save you money.
Yeah.
Yeah.
I'll talk about big picture. The concept is all of this would be in the Shield product. We can already collect test results. So getting all of the results and classifying failures and doing all of that, I actually, all of this is in the product today. What's in the product tomorrow, sometime in the future when somebody needs it, is this Bayesian and Gaussian math. So I can do it today. We could do a project. We could implement it. The platform is a database. So if I
Yeah.
update a failure rate in one place in the hardware standards library for 500 pressure transmitters, I just updated 500 SIL calcs. I don't have to go to each one. I don't have to touch them. I just run reports on pass fail. Same thing with the test intervals. I can bulk edit the test intervals and make them 12 months, 24 months, 36 months, and all 500 calcs just magically run, and we look at pass fail. So it's very rapid having this failure rate, not having to go into individual calculations and change it for transmitter A and transmitter B and transmitter C and valve A and valve B and the logic solver. All that is bulk editors. So being able to play what if, calculate these failure rates, and then decide pass fail and what does it mean to me is very, very rapid with regards to doing your administrative MOCs and making business decisions on moving this out. And we'll talk, we'll go back to your slide, John, about the 4 steps to savings. And then when we end up, we'll come back and look at some ROI calculations. And actually, the savings are significant if we do this. And it's kind of interesting now, right? Instead of functional safety being in a floodplain insurance, do this so you don't blow the plant up. And your plant manager is looking at you going, well, we've never blown the plant up. Well, do this so we don't go to jail. Well, nobody's gone to jail. Well, but I want to do it. Well, yeah, it's great. World's on fire. Things are happening. We're not spending this year. If you can go in and say, I can save you money. And oh, by the way, we'll do some
It's a different argument, isn't it? It's not the safety argument. It's the
you got hard savings here. So
it's the money
pretty
argument.
Exciting. You know, now all of a sudden, functional safety is a profit center. Wink, wink, hint, maybe. Yeah.
We're not used to that. Yeah. So 4 steps to savings. Let's we've got about 10 minutes, Mike. So let's
sure
see if we can cover these. So first 2 steps.
So this is overly simplistically. You can put all 4 up there if you want.
Okay.
This is that long, detailed flow chart we did, the approved vendors list. This is just oversimplistically. You got to do 4 things. Review your existing instruments. Do your criticality review. Which things are we going to maintain? Which things are we going to run to failure? Review your test plans. If necessary, tweak your test plans to get alignments with proof test coverage. We want the same pressure test plan for every pressure transmitter we do. We don't want one for fire and gas, a different one for BMS, a different one for SIFs, different one for LiPo. Keep it simple, stupid. One test plan for all pressure transmitters important to the business. Make sure we have clear guidance on failure classification in bucket number 3. Bucket number 4, let's go calculate some numbers and play what if on test interval extension. Go save some money. It's that straightforward. All right. I'm going to show
return on investment. Yeah.
Yep. I'm going to show 2 slides. I'm going to do some more Excel.
Okay.
So share my screen, if you will.
I will.
Let's go. We'll do that one you're showing.
To the right one. Is that it?
All right. So what I've got is a wimpy little calculator. This is one I did early on. And it basically says, hey, and you could take this and go to your boss and say, this is potential savings. I've since polished it because this does not resonate with the CFO. So we'll do 2 flavors. The geeky engineer, unsophisticated on money, what I did way back when. And then I learned that we need to be able to talk money with the money people. You want to go to your CFO and get money to do this, and you talk SILs and SIFs and risk reduction factors. This is a U.S. colloquialism. I don't know if you've ever watched the Charlie Brown cartoon, John.
Yeah.
Do they play the Charlie Brown cartoon in the UK? The teacher in Charlie Brown, every time the teacher speaks, says, wah, 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 wah. You can never hear a word she's saying, or you don't know what they're saying. Well, that's what your CFO hears when you get in there and talk PFDs and risk reduction factors in 61511. They hear, wah, 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 wah. You want me to spend what?
They glaze over. Yeah.
Yeah. So we need to be able to talk money with the money guys and gals to make this work. So here is the wimpy one first. So let's just pretend we have 20,000 instruments. We have 20,000 instruments we're going to test in our organization. We currently test everything every 12 months because that's what we've always done. We've inherited that. That's what's going on. We want to see, if I could get a big chunk of these things to 24 months, man, that'd be fantastic. So what do we spend on an instrument tech? Whatever you want the number to be, $75 would be a US number. 20 years, we're going to test these in the future. 30 years, we're going to test these in the future.
That's a per hour value, is it? Yeah, per hour.
Yeah, that's a per hour value. And this is the rationalization. What instruments can we change to run to failure? So we could make that 10%, right? So let's just put this in. And what you'll see, if we have 20,000 instruments at our site or in our organization, we're currently spending 1.5 million bucks year after year after year to test instruments, spending 1 hour, not 2, 3, 4, which might be reality, 1 hour standing next to an instrument. So we can debate, well, is it 2 techs and that's 30 minutes? Is it 2 techs and it's 2 hours? What about time to get it in the shop, to get your stuff, get your drawings, wander out there, come back in?
Yeah.
I don't really care about all that right now, but I've got for 1 hour to test 20,000 instruments annually, I got $1.5 million in spend. If I do this over and over again without cost value of money, inflation, any of that stuff, we're gonna spend 45 million bucks testing instruments.
Yeah.
If we can optimize this and get a large chunk of this stuff to go from 12 to 24, cost of testing halves, we go from 45 million to 22.5 million. If we can delete 10% of this stuff or 2,000 instruments, it's another $4.5 million in savings. We just saved 27 million bucks by just collecting some data on instruments
Over a lifetime.
over the next 30 years.
30 years. Okay. Yeah.
Now I'm going to do this now with the your CFO way. So if you're doing it to appease the accounting folk, you need to do something different. So this is a net present value calculation, and this is year 1 through 12. I think I've got a 12-year spend planned here. And what this is saying is we have 20,000 PMs in SAP, and this was another example. There was 20,000 and change for a customer, 20,000 PMs, and this is their number right at
preventive maintenance activities.
Yep.
Yeah.
Planned testing, right? We know we're going to test
planned
this.
testing. Yeah, preventive maintenance.
And that's the number from SAP, and this is the dollar value in SAP of what we do. Year 2 is just this times inflation. So if we put inflation on this and do a net present value calculation, this magic company, which was only 5 plants, this was 5 plants. This is not 50 plants. It's not 500 plants. It's a small little entity. They're going to spend $53.9 million net present value using inflation and discount rates, testing instruments just like they always have. I put some very expensive cost of projects in here just to drive this. And so it's saying, hey, we're going to spend $2.4 million, $3.5 million, digitally transforming instrumentation and controls and how we test it. Well, that's a ludicrous number on purpose. I still have 18% ROI. These guys are going to say, what's my return? What's my return on investment? They want to know when I'm cash positive. So there's a negative hit for the project in year 1 of minus 285,000 bucks. We're short, but I start saving money in year 2. So if I have generally an ROI greater than 10%, management's very excited. If you're cash positive in 2 or 3 years, management's very excited. And I've got 2 bites of the apple in here. We have 20,000 PMs. In year 1, 2, and 3, we've got a rollout where we're going to roll out this program across these 5 sites. It's going to take some time to get it out. And we were going to actually get test data back from the testing program. And so this is rationalization. And this was a conservative estimate that says we think we can get 5% of the stuff run to failure in year 1, another 5% run to failure in year 2, another 5% in year 3. So we think we're testing 15% too high of stuff that we don't need. And that's something we got to validate as part of the pilot.
Yeah.
So I'm knocking my annual PMs down to 17,148 versus 20,000 just by going through the rationalization exercise, writing my approved vendors list program, rationalizing what we test today. And now it's saying we don't have statistically valid data. This is very conservative assumption until year 4. And 4, 5, and 6, we're going to yank some stuff out, and that was magically 20%. So we're going to be able to only extend testing on 20% of the stuff. So if I can delete 15, extend 20, my annual PMs, preventive maintenance things that I have to deal with, drops to 13.9. So I go from 14,000, from 20,000 to 14,000. I'm saving the organization 9.8 million. What this intent was to under promise and overperform. We truly felt like that this is going to be, they have a lot of high pressure close a valve. So if I can really extend, this is saying if I can move 45% of their stuff out, well, now I'm saving 15 million bucks. I got 28% ROI. I'm still, cash positive in year 2. So if we start looking at this, what we ended up doing is we went straight to the board with this. They had a board for these 5 sites, presented this business case. And what ends up happening is now I'm also going to have SIL calcs and SRS and cause and effects and proof test plans for all this stuff. We're going to have live barrier health. We'll be able to see time in bypass. We'll be able to see excessive demands. We'll be able to see failures. We'll be able to see on-time testing. So we're delivering a 61511 compliance engine as part of that in this project with $15.5 million in savings. All of a sudden, this thing is paying for itself. We just got to go after the critical instrumentation program as the funding mechanism. And depending on what your management wants to hear, we're either making you safer and, oh, by the way, saving money, or, oh, by the way, we're saving money. And management wants to hear real savings, right? They want to hear scaffolding we're not putting up, third-party contractors we're not paying for, overtime we're not paying for. This is hard savings. This is testing we're not performing. It's not like I still have a job. I still work there every year. And instead of doing SIL calcs for 10 hours a calc, I do it in 0.1 hour a calc, but they're still paying my salary. That's a soft saving, productivity gain. These are hard savings. This is the stuff management wants. And that's the problem we've always had is functional safety has always been seen as an expense, a compliance expense.
Yeah.
And
but here, so just for clarity of the folks on the call, this is not just your safety instrumented functions we're talking about. This is preventive maintenance of any instrument.
This is any instrument you test today. You're doing this today right now. You're going to go spend $50.9 million testing instruments because that's what you're doing today.
You're already doing it. Yeah.
You're already doing it. There's nothing new. There's no impact to the business. All we're saying is, can we reduce that?
And the reason it's so costly is you're having to do it at a frequency which you've not justified in any way.
Correct. It's prescriptive.
Yeah. It's prescriptive rather than
prescriptive.
So this is a calculated. Yes, this is okay to do this at a different interval, and that's going to save you money.
Spot on.
Yeah.
While we don't need SIL calcs for all this stuff, and this is a little commercial thing as well, it's really fast to set up a template for an alarm with operator action for a pressure transmitter. You engineer that one time, and then you just populate that. You load smart plant data or Aviva data and instantiate, and it's done in seconds. And no one has to think. And guess what happened? There's a reliability model in that. So every one of these things gets built out with a mini little reliability model. If we have 20,000 pressure transmitters in there, I change the failure rate in one place, all 20,000 calcs updated. We run sensitivity analysis on going from 12 months to 24 months to 36 months. The CENTEF document does a really good job of rules of doubling, and I would massively, highly encourage that. If the math says go straight to 20 years, well, we don't want to do that. We want to go from 1 year to 2 years, collect more data. We want to go 2 to 4, collect more data. When we start seeing higher failure rates, you're going to want to back down and say, well, 3 is the right number or 2 is the right number. You're going to want to have a clamp that say we don't want to go past 5 or 7 or whatever the number is without administrative MOC, because you can get benefits from testing. So for instance, if we're checking for plug taps and we pump up the transmitter with a pressure source, and when we're done, we open up the root valve and we equalize pressure, we're blowing down that tap. So you're getting testing benefits every time we test. So if we go from annual testing to once every 20 years, we might see 90% of our stuff with plug taps in that service because we didn't think about the testing benefits. Same thing with a valve, the nasty fouling service. If you're doing a full stroke of a valve annually, well, you're cleaning seats. If we go straight to 20 years with it, you might have valves concreted and gunked up such that they can't close fully, and now you're screwed and you've got a hazard. So it's back to collect data. No matter what the data says, only double. Collect more data. If the data still says you can move it out, double it again. And at some point in time when the failure rates start to increase, you're going to back it off, and that's your magic number, if you will. That's where we want to run these things at. So there was a lot of mystery and magic on the math, which I don't know if the Excel helped or hurt that. It's straightforward. You guys can do it yourselves. And the other thing is the cost basis. If anybody wants to talk about this cost basis stuff, reach out to you, John, get us the link on it.
Please, if anybody wants to discuss any kind of pilot project, or if you want to discuss collecting failure rates to the point where you're actually producing your own prior use data, then we'd love to hear from you. And contact either of us, but you've got both the contact details up there.
So
I'm
the
gonna
takeaway is it's easy, right? It's easy to
takeaway
do
is
this,
easy. Yeah,
terribly straightforward,
yeah,
and you can get a business case that might excite your management.
yeah, yeah. The formulae, yeah, might look complicated to start with, but then you get them in an Excel spreadsheet, and they're not that complex to implement. So I'm going to just spotlight Mike. You probably won't be able to see these,
Sure.
but for everybody else, so going to the Q&A now for those who are still with us, we've still got about 20 odd people left, which is good. I think we had more at the start, but that's probably people disappearing. If you want to come back and see these questions, they will be in the final video, but yeah. So the first one is from Roman. I'm not sure how to pronounce that. He said, sharing is caring, especially regarding safety. I would love to see concerted effort from manufacturers to collect and maintain actual usage data from their customers. Yeah, we talked that. Then he says, is any device manufacturer actually committed to such an effort? Yeah, I'm not sure that we've got that many manufacturers on this call.
No, and they have, in theory, they will. It's proven in use, right? But
Yeah,
if it's a $500 widget, you throw it in the trash can and they don't know about it. So
yeah. I was
you've
going
got
to
to be
say
committed on your end to sending them the things that fail. And if they're just going in the trash can because they're
yeah.
cheap, they don't have a full data set.
So Roma, if I'm saying your name correctly, apologies if I'm not. If you watch the first video back, the one we did in end of January, we did kind of discuss this a bit. The collection of failure rate data, obviously for manufacturers with really expensive devices, is potentially something that's interesting and useful, but in many cases, not all of those. Not all of that data is available because they don't capture it all.
And they still won't know unless they give you a big giant thing about, were you in nasty fouling service? Were you in Saudi? Were you in Alaska? Where was this? How'd you install it? They've still got it. They'd have to get a taxonomy collected consistently from users to get an idea. How does my stuff do in clean service, dirty service, high humidity, high heat, high salt?
Yeah.
So.
Yeah, more difficult for the manufacturer for sure.
Yeah.
The second one is from Scott Abraham. Pros and cons of Bayesian versus Gaussian calculations. I'll leave that one to you, Mike.
I know, Scott. So Bayesian works really well for limited data sets.
Okay.
I'd highly, highly recommend you go after the Bayesian when you're first starting out. I think if you have 15 years worth of failure rate data, the Bayesian and Gaussian is going to give you the same numbers. So it won't really matter. But what ends up happening is you're going to get less. It's going to start with that initial assumed failure rate, wherever the basis is, one you made up or one you got from your OEM. And it's going to not let you go haywire from that number initially until you get enough data. So you'll get bites of the apple, coarse and fine adjustments on the numbers. So the Bayesian's the way to go if you're just starting out. If you're shell and have a gazillion hours of failure rate data, Gaussian is going to be fine for you.
Yeah.
I'll build both in the application. If somebody's ready for data, I'm waiting for somebody to say, I need it. We'll go roll it out. But if not, that's why all these Excels are here. I was playing what if on business cases and business logic. But yeah, Bayesian would be the way to go for anybody that's starting the journey.